Now we're going to look at problem 925. And problem 925 is slow-moving neutrons have a much larger absorption rate in 235U, so that's uranium-235, than fast neutrons produced by U-235 star. That star means it's in an excited state. By U-235 star fission in a nuclear reactor. For that reason, reactors consist of moderators to slow down neutrons by elastic collisions. What elements are best used as moderators? And explain. So what we want to do, we want to slow down, neutrons as much as possible, so they get more readily absorbed by U-235. So what we have is this elastic collision, and so what we want to do is minimize V1. So we have U-235, you know, that thing's big, and we have some neutron that's coming in here, but when it's really fast, this doesn't really get absorbed, and so we don't really have further fission. So what we want instead is this neutron coming in really quickly, and then it hits some unknown object. This unknown object recoils, and then this goes at some slower speed, and then hits the uranium. And then this can allow for fission. Okay, so this is our initial velocity, or initial, I guess, U1. And so what we want to do is minimize V1. So T1 is 1/2 mv1 squared. So that's going to be the resulting speed after this interaction. So what we can look at then is T1 over T0. This is 1 minus 2 m1, m2 over m1 plus m2 squared, 1 minus cosine theta. So we can't control theta very well. And that's going to be, you know, pretty obvious, because this is going to be some sea of neutrons that are hitting a whole bunch of the, you know, a sea of these particles that are slowing down to hit uranium, and uranium is going to be in some, you know, solid shape. So we can't really control theta. So this is kind of unknown, but we want to minimize T1, this kinetic energy after this interaction. Conversely, we can also think of this particle here going to have mass 2, and that's going to have some velocity v2. And so we could also try and maximize T2. And this is 4 m1 m2 over m1 plus m2 squared cosine squared eta. Right? So either one of these is fine. So either we want to maximize T2, I should say, not M2, T2, or minimize T1. Okay? So either way, we want to maximize T1, or maximize T2, or minimize T1 with respect to M2, because that's going to be this thing that is dealing with our, that is recoiling. So either way, we're going to have T1 by dt1 by dm2. And this is going to be negative 2m1. And oh, actually, we'll have a cosine theta. 1 minus cosine theta d by dm2 of m2 over m1 plus m2 squared. And this is going to be minimized, so this is going to be 0. Or we can have dt2 by dm2, and that's going to be 4m1 cos squared eta dm2 by dm2, I guess I should say d, and it'll be m2 by m1 plus m2 squared. But this is also going to be an extremum, and as you know from chapter 6, whenever this is an extreme, this derivative is going to be 0. So either way, they're equal to 0. And now you notice that we have these prefactors out front. That's either minus 2m1, 1 minus cosine theta, or 4m1 cosine squared eta. Either way, because these are both equal to 0, these don't matter. So what you get is negative, well, you get d by dm2 of m2 m1 plus m2 to negative 2 is going to be m1 plus m2 to negative 2 plus m1 to negative 2, or times negative 2, m1 plus m2 negative 3, that's equal to 0. And so we can multiply both these terms by m1 plus m2 squared. And so we get 1 equals 2m1 over m1 plus m2, or m1 plus m2 equals 2m1, or m2 equals m1. So what that means is that T1 is minimized, or T2 is maximized when the m of the mass of this neutron equals mass of this this absorber. Okay, but mass of the neutron is basically mass of a proton, and so this is approximately mass of the proton. And so what we want is some kind of hydrogen atom to absorb this.